Hello friends, I welcome you in lecture number 22 on graph theory. In this lecture we are going to discuss about adjacency matrix. We will see that how to represent a graph using its adjacency matrix. So to understand the definition of adjacency matrix, first we consider this example. Use an adjacency matrix to represent the graph shown in this figure. Whenever we want to write down the adjacency matrix for a given graph, first we have to determine the number of vertices of a given graph. Here we can see that there are A, B, C and D 4 vertices in a given graph. So remember that if you have n vertices in a graph, then adjacency matrix is a square matrix of order n by n. Here I have 4 vertices, therefore my adjacency matrix will be of order 4 or of order 4 by 4, that is 4 rows and 4 columns. Now how to write down that 4 rows and 4 columns of this square matrix? So for that, first we have to give these vertices a particular order. We have to list the vertices in a particular order. For example, we can write down our vertices as A, B, C, D, or we can write down in this order also A, C, B, D. So there are several orders possible. Out of those several orders possible for listing of vertices, we have to write down particular order. We have to determine that which order we want to use. For different listing of vertices, we will have different adjacency matrices for the same graph and all are valid. So here I am taking this simple order A, B, C, D, here A, B, C, D. Now because we want to write down 4 by 4 matrix, we have to determine 16 entries for this square matrix. So remember this formula or rule to determine the entries of adjacency matrix. For example, if I want to write down the entry corresponding to A and B, that is this entry, then that entry is equal to the number of edges from vertex A to vertex B. That we have to decide from the given graph. We have to determine the number of edges from vertex A to vertex B. So now we can see in this graph that there are 3 edges from vertex A to vertex B. Therefore this entry is 3. This is simple rule or formula that if you want to write down entry of a adjacency matrix, then check that that entry is corresponding to which 2 vertices and then write down the number of edges joining this vertex to this vertex. Now if I want to write down this first entry, then I have to decide the number of edges from vertex A to itself, that is 0 here. There is no loop at vertex A, or there are no edges from vertex A to itself, therefore we will write down 0 here. Now for this entry I have to determine the number of edges from A to C. Here we can see that there is no edge from vertex A to C, therefore number is 0 here. Then the number of edges from A to D are 2 edges here from A to D, so we write 2 here. Same thing I have to do for all the 3 remaining rows. So for this second row we start with B to A. So again it is clear that there are 3 edges from B to A also. There is no loop at B, that is there is no edge from B to B itself. There is one edge from B to C, therefore we write 1 here. There is one edge from B to D also, therefore we write 1 here. Now we check from vertex C. How many edges are there from C to A? there are no edges from C to A, therefore this entry is 0. What are the edges from C to B? There is one edge from C to B, therefore we write 1 here. And there is one loop at C. There is an edge from C to itself, that is a loop at C, and therefore this number is 1. From C to D there are 2 edges, so this number is 2. Then we check for vertex D. From D to A also we can see that there are 2 edges from D to A. From D to B we can see one edge from D to B. From D to C also there are 2 edges, so we write 2 here. And there is no edge from D to itself, therefore this number is 0. So you can see it is very easy to represent a graph using its adjacency matrix. Now what happens if I change this listing? If I change the listing of vertices or order of vertices, then I will obtain another different adjacency matrix, and that is also valid. So that is your choice which listing you want to use. Suppose I want to use D, B, C, A, then here also I will write D, B, C, A. Then here first I have to decide that what are the number of edges from D to D. There is no edge from D to D, so I write 0. Then from D to B, from D to B I have one edge. From D to C I have 2 edges. From D to A also I have 2 edges. Similarly I will write from B. From B to D I have one edge. From B to B no edge. From B to C there is one edge. From B to A there are 3 edges. Then from C to D there are 2 edges. From C to B there is only one edge. There is one loop at vertex C. And from C to A there is no edge. Then from A to D there are 2 edges from A to D. Then from A to B 1, 2 and 3 edges from A to B. Then from A to C, from A to C there is no edge, and from A to A there is no edge. So using another order of vertices I obtain another adjacency matrix, and this is also adjacency matrix corresponding to this order of vertices. So you can see that whenever we choose particular order we will have different adjacency matrix for the same graph. So in your examination you can choose any arbitrary order and write down your adjacency matrix. Because there are 4 vertices here, there are 4 factorial different orders possible. Therefore there are 4 factorial different adjacency matrices for the same graph, and all are correct adjacency matrices for the same graph. Now if you are clear, then we can understand this definition. Let G equal to VE be a graph with n vertices. Suppose that the vertices of G are listed arbitrarily as V1, V2, Vn. The adjacency matrix of G with respect to this particular listing of vertices is the n by n matrix, capital A equal to Aij, where this ijth entry Aij is the number of edges joining the vertex Vi to vertex Vj. Aij is the entry which is equal to the number of edges from vertex Vi to vertex Vj, and this number we have to decide from the given graph, and I have written this example. Now you can notice that here entries are symmetric with respect to the main diagonal. These 2 entries are same. Similarly you can see these entries are same. Then 1, 1, 2, 2. Then you can see these 2 entries are equal. So we can say that our matrix satisfies this condition: ijth entry and jith entry are equal. Here also we can see that if we consider these entries, they are same. This entry is nothing but entry in first row and second column, and this entry is entry in second row and first column. They are equal. Same thing for this. You can see this is entry in second row and fourth column, and this is entry in fourth row and second column. Both are equal. So the matrix which satisfy this condition is called symmetric matrix. So we can see that if our graph is undirected graph, then its adjacency matrix is always symmetric. And another way to determine whether the matrix is symmetric is, first you consider the main diagonal, and then you consider the lines perpendicular to the main diagonal. Suppose you observe these lines which are perpendicular to the main diagonal, then you can see that entries are symmetric with respect to the main diagonal. The entries on this line are symmetric with respect to the main diagonal, and that is the property of symmetric matrix. So remember, whenever we are writing the adjacency matrix for an undirected graph, then it is always symmetric. So that is cross check. If our graph is directed graph, then it may happen that if there is an edge from vertex A to vertex B, then there is no edge from B to A also. So in the case of directed graph, it is not always necessary that adjacency matrix is symmetric. I have taken another example. Use an adjacency matrix to represent the graph shown in this figure. So here also we can easily write down the adjacency matrix. There are 4 vertices here, A, B, C, D. So we can use this listing of vertices A, B, C, D, and then adjacency matrix is a 4 by 4 matrix. Now I have to check whether there is an edge from A to itself. No edge from A to itself. There is one edge from A to B. There is one edge from A to C, and one edge from A to D. Again there is one edge from B to A. There is no loop at B, so we write 0 here. From B to C there is one edge. There is no edge from B to D. From C to A there is one edge. From C to B also there is one edge. There is no loop at C, so I write 0. From C to D there is no edge. From D to A there is one edge. From D to B there is no edge from D to B, so we write 0. From D to C also there is no edge, so I write 0 here, and here also I write 0. And if you observe, this is undirected graph having no loops and no parallel edges. There are no loops and no parallel edges in this graph, and therefore it is a simple graph, simple undirected graph. And whenever our graph is simple, it will have no loops, and therefore all the entries on the main diagonal of adjacency matrix are 0. If given graph has no loops, then main diagonal entries are always 0. And another thing is, if there are no parallel edges between vertices, then entries of the adjacency matrix are either 0 or 1 only. That is, adjacency matrix is a 0-1 matrix if there are no parallel edges in the given graph. And this type of matrix is known as bit matrix, or another name is Boolean matrix. So if there are no parallel edges in the given graph, then its adjacency matrix is a Boolean matrix. So these are some remarks related to this adjacency matrix. The adjacency matrix of a simple undirected graph is symmetric. If a graph has no loops, then all the entries of the main diagonal of adjacency matrix are 0. If a graph has no parallel edges, then the entries of the adjacency matrix are either 0 or 1. And any matrix whose entries are 0 or 1 is called a bit matrix or Boolean matrix. They can ask you the definition of Boolean matrix or bit matrix also. So remember this definition: a matrix whose entries are either 0 or 1 is called a Boolean matrix or bit matrix. And if graph has no parallel edges, then its adjacency matrix is a Boolean matrix or bit matrix. Sometimes they can give you the adjacency matrix and ask to write down the corresponding graph with respect to the ordering of the vertices. Here ordering is given, that use this order and write down the or draw the corresponding graph. So here we can see order is A, B, C, D, A, B, C, D. Suppose I want to draw the graph, then I will require 4 vertices. So suppose these are the 4 vertices which we denote by A, B, C and D. Now we have to decide that which vertices are joined by an edge. So that will be clear from these entries. These entries are nothing but number of edges from one vertex to another vertex. So suppose we start with vertex A, then there is no edge from A to itself, that is there is no loop at vertex A. There is an edge from A to B. So I will join A and B. There is an edge from A to B. Similarly, this 1 means there is one edge from A to C. So I will join A and C. And 0 means there is no edge from A to D. Then we come here. This 1 means there is one edge from B to A that we have already drawn. There is no edge from B to B, that is there is no loop at vertex B. There is no edge from B to C. And there is one edge from B to D. That is I have to join B and D. From C to A there is one edge that we have already mentioned here. From C to B there is no edge. From C to C also there is no edge. From C to D there is one edge. That means I have to join C and D. Then we check for vertex D. From D to A there is no edge. That is we will not join D and A by an edge. From D to B there is one edge that is already drawn here. From D to C also there is one edge that is drawn here. From D to D there is no edge, so we are not considering loop at vertex D. So this is the graph corresponding to this adjacency matrix with respect to ordering of the vertices in this way. So they can ask you to write down the graph corresponding to given adjacency matrix also. Now if our graph is directed, then it is not necessary that adjacency matrix of directed graph is symmetric, because if there is an edge from vertex AI to AJ, it is not necessary that there is an edge from AJ to AI also. Here I have taken one directed graph and we can write down its adjacency matrix. So for that, suppose we are choosing this order of vertices V1, V2, V3, V4. Here I write V1, V2, V3, V4. and keep in mind that our graph is a directed graph. First I will check for V1, so whether there is any edge from V1 to V1, that is whether there is a loop at V1. So there is no loop at V1, so we write 0 here. Then I have to check whether there is an edge from V1 to V2. So we can see there is an edge from V1 to V2 and it is only one edge, so I write 1 here. Then from V1 to V3, so there is no edge from V1 to V3, so here I write 0. Okay, there is only one edge starting at V1 and that is going up to V2. Then from V1 to V4, so there is no edge from V1 to V4 also. Then I check for V2. From V2 to V1 there is no edge. So you can see here there is an edge from V1 to V2, but from V2 to V1 there is no edge. So here I am writing 0. There is no loop at V2, so I will write 0 here. From V2 to V3 there is one edge, so here we write 1. From V2 to V4 also we can see one edge, so this number is 1. Then from V3 to V1, so we can see one edge starting from V3 and ending at V1, so this number is 1. From V3 to V2 also there is one edge, I will write 1 here. There is no loop at V3, so we write 0 here. And from V3 to V4 there is one edge, that is this number is 1. From V4 to V1 we can see one edge from V4 to V1. Then from V4 to V2 there is no edge from V4 to V2. From V4 to V3 also there is no edge and there is no loop at V4. So now you can see that this is the adjacency matrix for this directed graph, and you can see it is not symmetric. These two entries are different. So if we have undirected graph, then adjacency matrix is always symmetric, but that is not true for directed graph. So sometimes they ask questions related to adjacency matrix. This was one question related to adjacency matrix asked in GTU Winter 2022 exam. Define adjacency matrix. Find adjacency matrix for the graph given in following figure. So we can write down the adjacency matrix for this graph. Before that we have to count that what are the number of vertices A, B, C, D, that is 4, 5 and 6. So here number of vertices are 6, therefore our adjacency matrix is of order 6. So I will have to write 6 rows and 6 column A, B, C, D, E and F, and same thing here also A, B, C, D, E and F. And we start with vertex A. There is no loop at vertex A, so I write 0. There is one edge from A to B, so I write 1. And there is no edge from A to C, from A to D, from A to E and from A to F. From B to A also there is one edge. From B to B there is no edge. From B to C we can see two edges, so here we write 2. From B to D there is only one edge, so this number is 1. From B to E there is no edge. From B to F there is no edge. From C to A there is no edge. From C to B we can see two edges. From C to C there is no edge, there is no loop at vertex C. From C to D there is one edge. From C to E there is no edge. From C to F there is no edge. Then from D to A there is no connection between D and A. From D to B there is one edge. From D to C also there is one edge. There is no loop at D. from D to E there is one edge and there is no edge from D to F. Then from E to A there is no edge from E to A, there is no edge from E to B, there is no edge from E to C, and there is one edge from E to D. From E to E there is no edge. From E to F there are 1, 2 and 3 edges. From E to F there are 3 edges. There is no edge from F to A, from F to B, from F to C, from F to D, and there are 3 edges from F to A, F to E, and there is no edge from F to itself. So this is the adjacency matrix for the given undirected graph, and we can check whether it is symmetric or not, that is cross check. And we can observe that there are no loops in this graph, therefore all the entries on the main diagonal are 0. And we can check the entries on the lines perpendicular to main diagonal, they must be symmetric. So if I consider this perpendicular line, I can see the symmetry. This is also same 0 and 0. Here I have 0, 2, here I have 0, 2. Then I can see that here also I observe symmetry. So we can see that entries are symmetric with respect to main diagonal, and therefore this is a symmetric matrix. Therefore our answer is correct. You don't have to show all these things, this is just for understanding, and we can remove this. You have to check after writing adjacency matrix, you can check whether the adjacency matrix is symmetric or not. And if your graph is undirected and adjacency matrix is not symmetric, that means you have made some mistake. Similarly, you can check that if there are no loops in your graph, then all the entries on the main diagonal are 0. So this is a cross check for adjacency matrix. Otherwise it is very easy to write down the adjacency matrix. So I hope you are able to understand that what is adjacency matrix for undirected graphs as well as for directed graphs, for simple graphs as well as for multigraphs. So we will continue with this series of graph theory in upcoming lectures. Thanks for watching.